Good afternoon, and thank you for joining today's webinar titled Improving Performance and Efficiency with Analytics, presented by SuEZ Water Technologies and Solutions. My name is John Nelson. I'm the Vice President of Operations, Sales, and Marketing at BBI International. And joining us today is Dan Walter and Greg Hoffpauir from SuEZ. Dan presently serves as an engineering and commercial leader for the biofuels and grains vertical at SuEZ Water Technologies and Solutions. And Dan has served many industries, including ethanol, wet corn milling, food and beverage, power, steel, chemical, and refining. He has presented numerous papers at technical seminars and for trade organizations in the paper and ethanol industries, primarily focused on energy management and continuous improvement processes. Dan holds a BS in chemical engineering and has more than 35 years of experience within the industry. Second up, also speaking today, is Greg Hoffpauir. He presently serves as the marketing leader for the biofuels and grains vertical at SuEZ Water Technologies and Solutions. Greg has worked in sales, marketing, and engineering roles in the following industries. He's been in ethanol, specialty chemicals, petrochemicals, as well as manufacturing. He holds BS in chemical engineering and has more than 24 years of experience inside the industry. So before we hear from Dan, who will be speaking here first, there are a couple housekeeping items that we do want to cover. First, today's webinar is recorded and will be made available. That recording will be made available within 48 hours on ethanolproducer.com. So if you do have some things that you want to review or you want to look at it again, it will be up on our website and available for you to review. Second, if you do have questions, and we hope you do, we encourage you to ask them, and you can submit them on your GoToWebinar questions tab on the right-hand side. Typically, it's on the right-hand side, but you can submit your questions. We will see them, and we will address those questions at the end of the webinar. And with that, I'm going to hand it over to Dan. Dan.
All right, John, thank you very much, and welcome everybody. Let's see, Tam, I believe I've got control now, yes? There we go. So today we're going to follow this agenda as we walk through our discussion. And I'll say right up front that much of the focus will be centered on stillage evaporators, but we're also going to be looking at the impacts of fouling and how modeling and analytics can be used to improve the performance of beer columns as well. We will try to leave plenty of time for Q&A at the end. And also, as John had mentioned, please feel free to ask any questions in the chat room throughout the webinar. Greg will be curating the chat room and we'll get any information back to you as soon as he can, or we'll queue up these questions at the end in the Q&A period. So let's get started. It's possible some of you have wondered, who are those guys? This company called SuEZ. My apologies there. I had a bounce. Get back here. Just a moment, folks. I'm getting myself in shape there. There we go. So SuEZ has been around for a long time, and in fact, it's a French-based utility company that specializes primarily in large private municipal water and wastewater facilities. Dating back to the early 1800s, it's actually one of the oldest continuously operating multinational corporations, and we did, as kind of in the picture there, we built a canal. That was the same SuEZ company in its early years. Over the years, they've acquired numerous equipment and other water treatment related entities with names many of you may recognize, including some of the businesses that came with the 2017 acquisition of GE Water that is part of SuEZ Water Technologies and Solutions now. Some of the companies are such as Degremont, Osmonics, Glegg, Xenon, Monsal, Sievers, are just a few of the businesses that are now part of SuEZ Water Technologies and Solutions under the umbrella of the larger SuEZ organization. Our history in the ethanol process space spans nearly 40 years, starting with efforts in gluten dewatering and fermenter deposit control programs, primarily in the wet corn milling space many years ago. Since that time, we've leveraged our core expertise in corrosion control, scale and deposit control, and separation technologies to develop a suite of products that support the challenges that face the ethanol industry. So before we get into the meat of this webinar, I would be interested in getting a little feedback from you, and we're going to do this a few times where we'll ask some questions and you'll have an opportunity to provide feedback answers. Everything will be anonymous. But I'm interested in your feedback on some bottleneck areas. And so if we queue up the first question on what production areas are most impacted by bottlenecks in your site. I'll give you guys a few seconds here to go ahead and click your answer and your response, and they'll all be collated for us here. And Tammy will have that information for us in a few seconds. I would play some Jeopardy music, but I don't have it queued up right now. But we'll give it about another 10 seconds here. Hopefully you know the answer to this one pretty quick since it's pretty general. All right, so how are we doing? You still getting responses in? If not, Tammy, if we can go ahead and pop up what we see.
Okay.
So here it is. This is kind of, it's interesting. This is kind of what we hear on a regular basis. So this crowd I would consider a representative group. Water balance is a big deal. And we're not going to be talking too much about water balance directly today, but we will be covering some things that may have an impact on it because they are impacted by evaporation operations as well. So we may actually be touching on those too. I appreciate the feedback here. This kind of level sets us so we're ready to maybe answer some of the questions you might have here. So let's move forward. As we get started, I want to take excuse me, I've already told you that part, but as I mentioned in the agenda, we're going to be focusing on evaporation and distillation. And that said, many of the concepts we discussed can be used to improve any process. It's measure, control, improve, predict, minimize. When I was with the GE, when they owned us, they used the acronym DMAIC, which is design, measure, design, measure, analyze, improve, and control. And as with any process, if you can't measure it, you can't understand it. And if you can't understand it, you can't control it and you can't improve it. So that's the reason we look at analytics so closely. Many of you have probably seen equipment conditions similar to some of the photos on this page. The pic in the upper left is representative of the typical evaporator deposits that form during normal operations. You see some plugged tubes, some debris that's in there. The four smaller shots down below are representative looks into Evap tubes using a borescope. If you note on the third one from the left there at the bottom, you can note some of the clumping of organic material that is usually the first step towards plugging a tube. The last in this series are just some of the other attendant challenges that can come with deposition and stillage evaporator systems. That's actually a completely plugged syrup line. It's kind of hard to move syrup through that piece of pipe right there. In the middle and at the right are deposits that are seen in beer column systems. The middle picture is actually looking into the bottom of a beer column, while the photo on the right is clearly a reboiler that's in serious need of cleaning and was down for a hydroblasting. Depending on your plant design, either evaporation or distillation is likely providing similar operational challenges, and it's possible even in some cases where both may be going on for your site, and we'll be talking about ways to address both of them. So to further clarify, while we're discussing evaps, we're going to focus on the 8-vessel double effect evaporator array that's common in the ICM design facilities. There are more of these type of evaporator systems in the US and through the Midwest here than any other single design. The temperature profile of these systems typically yields the higher temps in the evaps and in distillation, so the evaporators are temperature challenged as well. Whereas if you look at the triple effect, or excuse me, if you look at the steam driven distillation systems, that temperature profile is the opposite. Now, we know from experience with high concentrated organic solutions that fouling will be more severe at those higher temperatures. And so, in addition to the higher temps, these evaporator systems are 8 vessels in 2 effects. And so, selecting the right vessel can sometimes be a challenge since you have common inlet vapor and exit vapor lines that 4 vessels within each effect are going to be working against. So it's hard to tell which one may be the one that is in the most need of CIP, for example. And then if we just think about the job that evaporators are doing, we see this cycle of increasing solids going across the evaporators. Film will start forming on tubes. If it gets to the point, as we saw in that earlier picture, the tubes will constrict, they'll plug. That's going to reduce some heat transfer area. That's going to result in a need for more energy, higher level of energy over less heat transfer, which means increasing the temperature and pressure. More tubes will plug. You repeat the cycle, repeat the cycle, repeat the cycle. Pretty soon the system's going to come down and you're going to need to do more aggressive hydroblasting type cleaning actions. Now, hopefully this could be rectified through routine CIPs, but if those tubes are plugging, that more aggressive hydroblasting or mechanical cleaning is going to be required, because in a falling film evaporator system, once a tube's plugged, there's pretty little chance of opening it back up and gaining that heat transfer surface. So that's why it's pretty critical to try and stay ahead of things. So on the other side, as we get ready to look at the beer columns down the road, the steam-driven distillation system is that column, or the reboiler by design, is typically the highest temperature part of the system. That's usually where you see fouling in the steam-driven distillation systems. This will be more like a Delta T or Vogelbusch type of a design. And that fouling usually is the problem area. The evaporators typically are not as much of a problem, primarily because just the time between needing to take cleanliness actions on a beer column is such that the evaps, if there is any fouling, they have an opportunity to clean those at the same time, since the plant typically has to take an outage to do the beer column. Other things that can happen just in addition to fouling while it builds up in that column is you can also have some column flooding. You can have overhead vapor purity issues, and further downstream in distillation at the rectifier and such, where you can have some challenges if you're not keeping that system clean. So, based on this somewhat simplified view of the two areas where we're going to be looking in evaporators and beer columns, let's give ourselves a start on the evaporators. And what we want to start with is the end in mind. I'd like to use the following goal statement as our guiding objective. We want to run the evaps as clean, as long, and at the lowest total operating cost as possible. That's not rocket science. That's pretty straightforward how people want to run these things. The drive for this efficiency will include operating for the longest time between both CIPs and a complete outage-driven mechanical cleaning action that can reduce productivity and bottom line profits. I'm not advocating here that we just extend CIPs for the sake of trying to get more time between to save chemical money, on caustic or others. Instead, I guess what I would put this in is saying that what we want to do is only conduct CIPs where and when they're needed to achieve the optimal results. And we're going to look at ways that we can start to see that. The chart on the right kind of sums it up graphically. We want to operate in that clean zone. You can represent that by that the SuEZ green circle that's on the chart there, before any of the bad things take over. And the bad things we kind of talked about in some of the pictures: the excessive plugging, Once those tubes are plugged again, it's hard to keep them, hard to open them up just with the CIP. What we want is we want to see the evaps looking like those bottom two pictures on the left rather than the right. And think of how much better your evap systems run when they're coming out of mechanical cleaning and you know they're in that condition. That's where our goal should be to operate these systems. So let's think about evaporator performance in the perfect world. In a perfect world, the CIP on a schedule that hits the evaps most in need every time because fouling is predictably occurring at a consistent rate within each vessel. We'll not experience any process upset, such as power outages or high sugar firms or anything like that. And we'll have consistent production rates. We're going to run at X million gallons per year rate. We're going to have a constant thin stillage feed rate and all the other key process variables. In our perfect world, we'll have a continuous, highly efficient operation of the evaporator system where pressure differentials will never increase to levels that could either impact the upstream dehydration or downstream distillation processes. I'd like to say it's kind of like the mythical Lake Wobegon, where all the women are strong, all the men are good looking, and all the children are above average. That's the perfect world. Now, what we know is, in reality, we need to address issues that occur as a result of those truly normal operations. We will see power outages from time to time. We will see process upsets that may impact ethanol conversions, for example. We're going to see rapidly increasing steam pressures when these sorts of things occur. And it could even get to a point where it could impact the auxiliary systems, if you will, the dehydration up front or distillation on the back. Increased base losses can occur when you have your pressures coming off these systems dropping below 9 psi, for example. Or you could be slowing down dehydration because your pressure differential is so great, you're running 22 to 25 psia steam up front to keep up. So it's really important to try to stay ahead of the cleanliness actions as much as possible. Now, operations may keep up with the CIP schedule and even throw in a couple extras where they believe they're necessary. And chemicals may be used to try to stay ahead of the fouling, whether it's online or with CIP additives, for example. The challenges are tough enough when the system is operating at the design plant rate. The reality, however, is that today, in the competitive environment that we're in, most ethanol plants are running well above the designed operating rates. Now, most of the upgrades to allow this is like grind upgrades, additional fermenters, distillation improvements. That's made it possible even as the evaporator system remains the same size. I've not seen but one or two sites that have actually expanded evaporation as they expanded their plant. We know the systems were designed to be oversized in order to achieve manageable efficiency and cleanliness at that designed run rate with minimal downtime. Higher process rates have just, all it's done is placed additional stress on the evaporator system, making it even more important that you optimize those cleanliness actions. So in the real world, in order to achieve the goal of cleaner, longer evaporator runs, we need to understand where and when to CIP as a key in achieving the goal. I'd like to pose a couple more questions for the group, so I'll turn it back over to Tammy. The first one here is going to be just a kind of a statistical challenge question. For this ICM design, what is the statistical chance of selecting the right evap vessel most in need of CIP? Give me what you think it is, and then we'll go to the second question, and we'll take a look at this one. Just remember, we've got 8 vessels in a double effect array with common headers, common steam inlets, common vapor exits. All right, I don't know how, Tammy, how the questions are coming in, if they've slowed down and everybody's answered.
Give it about 10 seconds. Oh.
Did I do that? There we go. Well, interesting. The 12.5% is the winning number here. And from a statistical perspective, not knowing anything else about the system, that would be the right answer. But we have to recognize that we can look at DPs across each of the 4 vessel arrays. I would project 25% statistically would be what the correct value would be. 50% could be when you start to add in additional knowledge, and that's what their second question will be. If we can go to the next question, where what we're looking at is what drives your decision to CIP an evaporator. This may be the difference between 25% and 50% right here. So we'll give it about 10 more seconds here. 5 seconds. Quick, get those answers in to qualify. All right, Tammy, if we can get our results. And there we go. A combination, good. There is a lot of information that you have in your systems that should allow you to determine which vessels to select. Differential pressure is the most traditional way of evaporators and is very effective when we look at the steam-driven distillation type systems, delta T type plants, because that's a one-to-one multiple effect evaporator. So that delta P across an evaporator is going to give you exactly how well that system's running. A little bit more of a challenge here because you have 4 vessels that are all on the same headers, and we'll look into what can happen with that here in just a moment. But the right answer is combination of above. Learn from your system. That's good to see. That's what we would expect, and that's how most people are operating. Alrighty, thank you. If we can get back to the deck. And so now that we're done with our questions, if we think about most of the ethanol facilities today, they've got a pretty robust data collection, monitoring, and historian capability. We should be leveraging this information to help that all of the above decision process. It also will help us to develop some analytical tools and processes to drive improvement opportunities. Some of the basic data that can be used to identify these opportunities are the pressures and temperatures, operating logs for CIP solutions and solids and times, etc. But note that this is what I've got on the list here is just a small sampling of what may become important to driving predictable, methodical performance improvement. As we learn more about a system, additional factors may be added into the analysis, such as solution pHs, enzyme usage, backsets, etc. Are just a few more that might impact overall performance. As with any orienteering effort, in order to know where we want to go, we first need to know where we are, which means collecting and analyzing that data to identify and address the potential blind spots. So what we're going to do next is review some of these blind spots and just using the same data that you have at your disposal in an effort to understand and improve operational efficiency. So the first blind spot we'll cover will be using Evap dry solids profiling to determine the relative evaporation rates within the evaporation train. Now this requires doing dry solids testing on the thin stillage and each of the Evap vessels, plus a bit of mass balance mathematics to generate a relative evaporation rate for each vessel. The chart on the right shows multiple outputs of such testing on an Evap system that we've done in the past. What you see is actual evaporation rates for each vessel for 5 separate runs. These are done as a test, so it's just point in time testing. This is 5 separate times over a couple-week period. The information provides the ability to actually see the performance of each vessel, which are underperforming, which ones are doing the most work, and it gives you the opportunity to determine which vessel would be the best candidate for a CIP. It also will allow you to see the performance improvement from the CIP. For example, here in number 6 in these columns, you can see a CIP and the improvement performance that was seen within that vessel after a CIP. That is possible using a solids profile like this. The challenge with doing this is that the time required to conduct this testing can be about 4 hours worth of lab time when you take into account sample collection and the actual 3-hour dry time. You could also speed this up using the IR type rapid drying ovens and get it to a few minutes. The only caution I would note if you head down that path is that those devices provide results based on calibration programs that are developed within a relatively small range of the expected results. These are what are used to do thin stillage solids, for example, and syrup solids. If you were going to use it for an entire profile, you would want to set up some profile programs, or I should say some calibration programs between the thin stillage and the syrup levels to get more accuracy. Otherwise, you may be fooling yourself. Now, since I have the bully pulpit here, I want to also note that SuEZ has developed a system called Ivap that's an online monitoring and analytics package that can track this solids profile and all the associated evaporation rates on a real-time basis. It'll also help identify which vessels to CIP and predictably let you know when. Now, there's much more to Ivap than we can talk about here today in this session, but I would encourage you, if you're interested in learning more, to reach out to the SuEZ Biofuels and Grains team or your local SuEZ representative, and we can sit down and go over how it could help you. I mentioned a few slides earlier about the importance of CIP selection and its impact on system performance. The profile analysis like this can provide the information to see performance relative to each other and which one is in the vessel most in need of attention. For the next few slides, what I want to do is walk through what is actually going on and why this is so important to see what's going on in your evaporator system. So to demonstrate what's going on when you put a vessel in CIP, I'm going to simplify the conditions to make math easy and assume a bit of a perfect world distribution of vapor across 4 vessels in this theoretical effect that we have. What we're seeing right now here is that vessel or that system in a clean state. In this case, we're spreading 100,000 pounds an hour vapor across 4 second effect vessels and generating about a 4 psi-d differential. Since each effect has a common inlet vapor and exit line, the actual distribution of performance will follow the path of least resistance. So in this case, cleaner evaps will do more than fouled evaps, but they're all going to have the same DP across them. I know it's technically looks like a pretty large system, but I picked 100 to use it as a basis, because then we can look at each vessel and kind of think of it as percentages, and you can do quick math thinking about how it would work for your system. And also that 4 psi pressure differential in the clean system may seem excessive. It's just to kind of for the effect to see the difference between running clean versus running dirty, selecting wrong vessels. Your system's probably running closer to 2 psi when it's clean across each effect. So don't get hung up on that part of it, please. So in our clean system, during the operation over time, we're going to start to foul. It's just what's going to happen. With thicker liquor typically going to foul the fastest, we've all seen this as you get further down in that evaporator train and those solids start pushing upwards to 30%, you're going to get more fouling. As we can see here, that 100,000 pounds an hour of vapor is no longer equally spread. This is what happens when one of those vessels foul. It's going to be doing less evaporation. It's going to be making the other vessels pick up the slack if you're going to keep that rate. The only way it can do that is by increasing the pressure and temperature. They go together to generate higher heat flux across those heat transfer surfaces. And when that DP is going up, that is our evidence, as we saw back in the poll question. Pressure differential is key. that's the evidence that you're losing cleanliness, and that increased energy is required to keep it running. If we're measuring evaporation rates or even measuring the condensate production from each of these vessels, if it's consistent, we should be able to see that vessel 8 is performing at about half of what it should have been doing, half of 5 and 6, and only 60% of when it was absolutely clean. So logically, if we're saying, hey, we know what's going on here, let's pick number 8 in this case. What will happen when we do that, we're going to see an increase in the pressure differential for the effect right when you take that offline. I'm going to kind of call that the CIP pressure bump. In our example here, you can see that the pressure bump is about 0.3 psi differential increase when we took 8 offline. That's the result of trying to do the same volume of evaporation with effectively 25% less heat transfer available from going from 4 vessels to 3. The size of the bump's important. It's an important indicator of how foul the vessel removed may be or have been. A small bump like what we're seeing here would suggest the vessel removed wasn't doing that much of the work for that effect, versus a large bump, which would suggest exactly the opposite, that a high-performing vessel was taken offline and the fouled vessels were left to do the work. We're going to see that in just a minute. So while this is off and it's doing its cleaning, when we bring it back online, the DP is going to return to below that pre-CIP level. That's why we're doing it. Note that the second effect pressure didn't get back all the way to where we started originally at 4, because all the other vessels are still also experiencing fouling. It's just kind of a continuous operation. But we did get back to within a half a pound of the clean system. So we could say we recovered 75% of our fouling compared to when the system was clean. We're almost back to clean. With the ability to measure the evaporator at that vessel level, we can also track the cleanliness recovery in that vessel that we CIP'd, which can provide some pretty valuable information to CIP effectiveness, or if your loss of heat transfer is due to tube plugging, because if it's plugged, you can't get it back most of the time. So let's start back over again here, and instead of if we don't know exactly which one of the 4 are bad, we're going to look at the system to see how it responds when we can't identify that. For example, if we were to select vessel 6, which, as we know, is a vessel that is performing at the highest evaporation rate, what would be the impact? Why would we ever select 6? It may be as simple as it's that vessel's turn based on a calendar or a predetermined CIP schedule. But maybe we do 6. So let's see what would happen. If we do that, what we're going to see happen is we're going to redistribute that 30,000 pounds an hour that was in vessel 6 over the remaining 3 vessels. And remember, we already have a stressed out vessel there in 8 that is just going to continue to foul more and more at a higher stress. If we look at what the load was on our bump as well, we could see our CIP bump was 2.2 pounds. We, when we took that system off, saw a lot of pressure increase because we took a workhorse out of the play. And it's important to make sure that we understand what the implication of that may be if we want to understand whether or not we're going to taking advantage of our cleaning actions. And in fact, what we would see is it's possible that in many cases when we have that additional stress, that the result will be little improvement or possibly even an increase in the DP across that effect when we come back off the CIP. In effect, what we're saying here is that the system is in worse shape after that CIP than it was before. Now, why is that? It's essentially because we cleaned a clean vessel, and the remaining vessels were put at even higher stress and are even in worse shape than when we started to clean the clean vessel. That's why vessel selection becomes vital in systems already running at rates well above the design, like what we're seeing in ethanol plants today. Now, I went through quite a bit there. I want to just take a quick moment to just, remind everybody, if you have questions, please address them to the chat room, and we'll make sure we're collating them. And Greg can also respond to anything that he can answer right away for you as well. So here, just a quick review um, of what to watch for on CIPs and what those things can tell us, talking about the CIP bump. That large DP increase in the CIP, usually you see poor recovery. And you probably didn't, you didn't need to do that vessel. You probably could have spent more effort on a different one. And that only comes with understanding which vessels to be cleaning. Conversely, small DP increase usually looks like you're getting a good CIP cleaning, and you should see good recoveries coming out of it. You'll see higher recovery of lost pressure differential when you're cleaning the right vessel. You get the most that you can with a single CIP. Finally, you may see averages in between. Without any better knowledge or analytics, it's hard to say whether or not the CIP did anything for you. You may see very little improvement. You may be cleaning too often, for example, that can cause that. Collecting and analyzing this data can help identify what your history has been. This is a look back to do this, but it will help possibly identify some trends of how much longer you could go on certain vessels versus others, and allow you to get longer periods of time between CIPs. Remember, think run cleaner, longer. Now I'm going to go ahead and pop in that Ivap, that overt SuEZ commercial plug icon there again. All of this is also can be monitored and tracked with the SuEZ Ivap system. And in fact, what I have here are a couple of actual Ivap output charts for a system where we have the ability to measure individual vessel performance and trigger CIPs when a predetermined performance level is hit. The top chart here shows how, when tracking the actual vessel performance in real time and only conducting when the trigger says conduct a CIP, you can see that the time between CIPs is variable. It brings into question the efficiency of running based on any preset schedules. And also notice here, if you see on these charts, the amplitude of these spikes along the way, those are related to the CIP solution strength as well. So we can see if we have a bad CIP, for example, here, we get a short run. If we have a good CIP, we have a much longer run. It helps you troubleshoot whether or not your CIP process is consistent. And we'll talk a little bit more about that in our next blind spot. So again, self-promoting here. This also is, automatic within the SuEZ Ivap system. The bottom chart here is actually showing evaporation rates on a vessel and measuring the improvement in the flow. What we have here is an increase in the actual evaporator flow as it moves forward. So let's move on to blind spot number 3, which is our CIP process itself. So what we have here in our day-to-day work with ethanol producers, we found that the consistency of both CIP solution and the actual process cycle times can vary substantially from event to event within a single location, for example. Developing the discipline to optimize starts with developing a consistent, repeatable process that reduces that variability. Some critical times to check regarding CIP solutions are as follows. Some of these items. The solution strength is key. Make sure you have what you think you have and what you're targeting. Usually, we're targeting somewhere between 3 and 5% caustic solution strength. This is important in breaking down the organics that that caustic is there to remove. If you don't have actual high enough hydroxyl concentration, which is the OH part of the caustic, you're not necessarily going to have the 3 to 5% caustic solution you may think you have. This could happen if you're using processed condensate to make down or reusing CIP solution as part of your batch. You need to do more than just test for total alkalinity, which is a lot of times what labs are doing. Testing for the actual available hydroxyl is key to effective removal of those organics. And you want to make sure that is at the 3 to 5% of what you're shooting for. The CIP solution temperature is also vital. Cooler solutions will be less effective. I believe most CIP protocols are targeting temperatures above 170 degrees to 180 degrees. Are those temperatures being consistently achieved for each CIP? If you track that, you might start to see a correlation between CIP success and actual performance in the vessel itself. Now, regarding the actual process, it may be possible to optimize the step times to reduce the total CIP cycle time and get back to full strength operation sooner. I also want to point out here that if you're conducting a two-step CIP with an acid step following your caustic step, there are products available today, and yes, SuEZ does have them, that can address the removal of the inorganics that you use the acid step for, that won't be removed by caustic. This can allow a producer to eliminate that extra time and the acid, not to mention the reduction of the acid use and all the EHS aspects that come with it, and take care of both organics and inorganics in one step within your CIP. So I'm going to shift here for a minute and review some of why these evaporator deposits, why we're so concerned with organics, why we use caustic. We've sampled and tested hundreds of evaporator deposit samples, and what we're seeing is these deposits are typically made up of better than 75% of organic material. I guess it's really not unexpected when you think about what's in thin stillage. It's a lot of organic material. But no less important, a little lesser level, the inorganics, and typically magnesium phosphate and those types of scales will form due to the extremely high concentration that's coming in with the corn. There's a lot of mag phosphate that comes in with corn to the on the order of about 7,000 ppm. And if you think about in your evaporator system, that's going to concentrate up to over 35,000 ppm in the evaps. That's 3.5% in that syrup solution. We deal with solubilities of inorganic salts in water treatment all the time, and to get to that level of solubility is a good bet you're probably precipitating mag phosphate. Hopefully, it's coming out and it is part of the matrix with the organics. But what we see usually is you can't control it, and it's also going to come out and it's going to leave mag phosphate scales within the evaporator tubes. In addition to that, there might be some oxalic acids that are in those deposits as well, which will form and combine with calcium if the conditions are right to produce a beer stone, which is calcium oxalate. And as I discussed earlier, the products that SuEZ does have for these, there's a couple different classes that are there. These product classes include the inorganic deposit control that are designed to control the precipitation. As I mentioned, solubilities aren't as high as what the concentrations are. You may not be able to stop it, but you can control it. In addition, we have an organic deposit control product that's designed to condition the organics within the thin stillage. And I believe it may be the only one out on the market today. But this allows that the solids in the evaporators to flow more effectively. They clump up less, which reduces the chances for tube plugging. And what we see is when you CIP, the CIPs clean up better when you're dealing with those organics. The primary reason to feed these is to extend that time between CIPs while improving the heat transfer. Remember, run longer, cleaner, and more efficient. When you can extend that time and run higher efficient, more effective heat transfer, you're going to end up generating lower energy usage on a BTU per gallon of ethanol produced basis. So your evaporator essentially may help reduce your BTU per gallon efforts when you're starting to look at CI scores and other things that we see becoming more and more prevalent in the industry. So the reason to utilize the methods and monitoring we're discussing here is to support that, proving that if performance improvements can be achieved with such applications, the results and the associated economic benefits justify adding such products to the thin stillage or CIP solutions. And I will one last gratuitous plug here on the Ivap system, mostly because I mentioned that if you have questions or have an interest and want to learn more, you can contact anybody on the Biofuels and Grains team, and we can certainly work with you to see how a system like this may benefit you. We're going to move on now to beer columns, and so before I get started on it, I will again reference to the Q&A chat window. We just have a few more slides to go through, but if you have any questions over what we've covered on EVAPs already, please go over there and log them in. So as we reviewed earlier on the beer columns, when we start looking at steam-driven distillation, that beer column and the reboiler are typically the highest temperature area. And we can use some simple data and analytics to optimize these systems just by a straightforward regression analysis approach in order to characterize the operation and look at it over multiple operating cycles between cleanings. Now, what this will allow us to do is we'll collect data. It may be CIPs, the CIP timing, pressure differentials, steam to reboilers, etc., and we can use this to determine any changes by collecting that data, tabulating it, and then what we will do is run a regression analysis on the multiple runs to identify which variables are exerting the greatest impact on performance, as well as develop a current performance expectations. We could call this the baseline or the process capability, if you will. From here, what we have is the ability to determine if any process changes would be having a positive impact on column performance with the goal of increasing time between those CIPs. Usually an economic analysis can be conducted that'll help in determining what performance improvement would be required to justify any process changes, whether it's chemical feeds or equipment additions or any of that. Understanding where we are before deciding to go where we're trying to go. That's the goal here, part of the orienteering, as you recall. So here's a case where a deposit control program was developed and deployed in an effort to increase that time between beer column CIPs. And the resulting improvements on the baseline were easily measured to determine program success well before the end of this cycle. The same analysis can be deployed for operational changes such as specialty enzymes or to objectively measure the consequences of such changes on beer column cleanliness performance. The regression analysis can identify the performance improvement compared to how the column would have run in its original state. Ultimately, achieving a goal of longer runs between CIPs was actually pretty easy to capture. Either you get there or you don't. But by running the regression analysis, you can see if you're on the right track well in advance of the time. Now, we do feed the similar type products to these systems for the exact same reasons. You're typically looking more at organic fouling within distillation columns, though. So usually you'd be looking at the organic deposit line from a SuEZ perspective. And the reason for that is because the deposits, they're coming from the same stuff. I mean, we're talking about, the beer, which is just a few steps ahead of thin stillage. It's got all of the same actors in it. And so when we do deposit analysis out of reboilers, out of beer columns, what we see is the same and even higher amount of organic fouling that we're finding. And that's what we're trying to slow down in order to keep these systems running longer. So to close here, what I want to move to is a case history on beer columns here's the case of a producer who was averaging about 28 days between the beer column CIP actions. They wanted to extend the time in an effort to reduce that downtime and improve their column operation. They used to run longer, but now they're running harder. They're not getting as much time on this particular column. SuEZ, we proposed the Food Pro 9834, which is the organic deposit control agent. The system was monitored to ensure positive results were being realized from the beginning of the trial. And the results were a run length that was increased to 44 days on average, which is 5 additional days of production annually. And as a side note, in this particular system, while it was treated, we also saw cleaner beer column overheads. This site had been struggling with a little bit of fouling all the way through to the rectifier, and this helped clean up that as well. The bottom line for this application, after accounting for the treatment chemical cost, was a net savings, annualized net savings of $880,000. So it proved itself out, and through analytics, we were able to justify the program and generate the results this particular producer was looking for. So that's enough time on the presentation. I'm going to turn it over to Greg and John to open up the Q&A, and we'll get into that. So Greg, I know you've been monitoring the chat room. Do we have any open or important questions to get started?
Yeah, Dan, thanks. Kind of curious how the front end bolt-on process improvements that producers have been adding to their plants, how it's affected the evaporators, and what have we seen, or what have they needed to do on the back end, or how has those front end processes affected the back end?
That's a good question, and it's kind of interesting because that is, we talked a little bit about trying to get more out of ethanol plants, and a lot of the move now is to get higher value co-products that those front end bolt-on processes are helping to achieve. What's interesting is what we're noticing is that while you're cleaning up the thin stillage, if you will, reducing the amount of solids because of capturing those and getting a higher value product, when it goes into evaporation, what ultimately is occurring is the evaporator residence time is increasing by a factor of 3 to 5. And we talked earlier about that, like all these solids and the inorganics as well. The inorganics are still in that stream coming in, so that 7,000 ppm mag phosphate stream is not going to stop at 35,000. It's going to be closer to 140 to 150,000, or 14 to 15% of the ultimate syrup, which just puts even more pressure on the evaporator. So I would say that it would be more important to be monitoring as much as you can around that evaporator system, or you could end up in back-to-back trying to catch up and stay ahead on evaporation, even though you think you're putting in cleaner thin stillage. Time and temperature. It's all time and temperature.
All right, thanks. Another question here that came to mind was with the analytical tool, the Ivap that you've referenced, how have you seen it change what the producer is getting from a standpoint of their CIP frequency, or the amount of the accuracy, I guess?
Yeah, so I'd shown some charts earlier of an actual Ivap system in use, and in general, we have a number of these systems out deployed in the field already, and in general, I would say that we are seeing about a 30 to 40% reduction in the number of CIPs that are conducted right out of the top, just by being able to measure and understand when the right time is and predict when the right time will be for conducting CIPs. Some are doing better, some are doing a little bit less. All of them have seen a reduction in the number of CIPs. As far as the performance, what we are seeing is a reduction in the BTU per gallon on sites that are doing this, because they are staying ahead and keeping the heat transfer coefficient as high as possible. Certainly for a full year, and in some cases even beyond that, where some sites are going multiple years between conducting any mechanical cleaning.
So I just want to open it up to the attendees. If there's any questions, please enter it in the chat or in the question bar there. Add to what we've already got. Just another question is you hit on the EVAPs and the beer column. Where else have you seen these deposit control chemicals used within an ethanol plant?
Within the dry milling space, we have seen some of the boil out chemicals, for example, have been used to help clean up tricanters or disc stacks. You can see sometimes a buildup of inorganics and organic fouling there, and these can help with cleaning those systems as well. We showed the picture of that syrup line that was completely plugged. We do not apply these products with the purpose of trying to keep that from happening. But what we have heard is that it does not occur as often and they're easier to keep clean. You know, as I mentioned, we are conditioning solids with organic deposit conditioners. We're not eliminating them. There's just so much solids we're dealing with there. We're just trying to extend the length through. So any place where you see beer stone, like fermenters, mash coolers, the beer mash cooler in particular, where you have that mash cooling down, which will drive oxalate out. Those are places where some of these offline cleaners have been quite effective. And in fermenters, we have seen the use of online oxalate control where oxalate can be a problem. That's usually where you have oxalate problems, is up in fermentation.
All right, I'm just kind of waiting to see if there is another question comes in. I guess the other question that I'd like to, I think you've talked about a little bit, but if a producer was interested in an additional analytical tool, the Ivap analytical tool, what would be some of the steps that outside of contacting SuEZ that they would have to do? Is there a process for that?
Well, yeah. As far if we're talking about installation, that's one thing. It's a relatively simple system to install. It requires 2-inch taps with full 2-inch full port ball valves on each of the evaporator recirc lines, plus one on the thin stillage to get our analyzing our sensors to be able to measure what's going on. But probably what's more important is leading up to it is going back to the orienteering analogy, knowing where we are by looking at historical data to see what the opportunity may be for improvement. We like to approach this with a kind of a methodical process improvement plan where we're defining the process capability, initial process capability, and then develop any cost-effective improvements and whether or not we can raise that capability to achieve what could be a clean process entitlement. That's kind of a two-prong approach. We like to call it a 1-2-3 approach on defining, achieving entitlement, and determining effectiveness for improvement. But it's might be different for each site. It really depends on what their operating history is, what their goals and objectives are.
No, okay, thanks. As of right now, Dan, that's the last question I had on the list. I'll leave it open one more minute for anybody else that wants to ask.
If there aren't any additional questions, I guess I would just like to thank everybody on the phone here for attending today. And hopefully you jotted down the names of the SuEZ B&G team that was on one of those slides. Certainly, if you have any additional questions or want to learn more, reach out to your local SuEZ WTS rep or call any of those numbers and we'll do what we can to help explain more, show you more what's possible, and walk you through how it may or may not benefit your organization and your process. So that's it on my end. And Greg, anything else coming in?
No, that's it for right now, Dan. Thanks.
All right, I'm going to turn it back over to John. I think you've got some closing statements as well.
I do. Thank you, gentlemen. Dan, thank you for your insight. We appreciate you sharing your knowledge with us and our audience today. One question I did have for you guys is you talked about the numbers that were up earlier. Dan, if people do have some questions and want to follow up, is the best thing to do call one of those numbers? And if so, what was the number again? Can you repeat that, or an email?
Yes, I can. You have my name, Dan Walter, and our emails at SuEZ are pretty straightforward, dan.walter@suez.com. But I'll go through some numbers here as well. If you wanted to make the phone call, which I prefer old-fashioned phone calls, my business phone is 515-446-0049. Greg Hoffpauir, who's also a member of this team, I'll just give you his phone number because his name can be difficult to spell. I know it is for me. It is area code 309-574-0035. Brad Thompson is another account manager on our vertical team. His phone is 309-255-0192. And I should note that both Brad and Greg live over in call it the Western Illinois area. And then finally, there's Dan Jones, who's in the Cedar Rapids area. And Dan's phone number is 319-360-7101.
Great. I appreciate it. Again, on behalf of Ethanol Producer Magazine, thank you for sharing your insight. Today's webinar is recorded and will be available within 48 hours on the ethanolproducer.com website. And again, thank you to SuEZ for sponsoring and presenting today. A couple upcoming events that we have tomorrow at BBI International. We do have the Biomass Magazine's 2022 Editorial Outlook webinar, so you can get an idea of what's coming down the pipe for themes in Biomass Magazine. Same with Biodiesel Magazine. We have the editorial preview of what's going to be in our publication. That's going to be taking place September 30th, and get a little idea of the audience there. One note with Biodiesel Magazine, we will be covering quite a bit of renewable diesel, which has been a hot topic lately as well. So hopefully some people can join us for that. We also have our UAS Summit, that's Unmanned Aerial Systems, coming up in Grand Forks, North Dakota, and that's been going on for 15 years, and that's an in-person event. Military are free. And then we have our International Biomass Conference and Expo taking place in March. So hopefully some of you can join us for that. Again, we do cover advanced biofuels on that agenda and in that program. So we definitely would ask that you take a look at that. And then we have our International Fuel Ethanol Workshop scheduled for June 13th through the 15th in Minneapolis, Minnesota. And co-located at that event, and new this year, one of the hottest topics we're finding in the ethanol industry is carbon capture and storage. So we hope you can join us in person for those events as well. And again, thank you, Dan, for your insight. Greg, we appreciate you guys being a part of our webinar series. And to all the attendees, thank you for joining us, and have a wonderful afternoon.
Thanks, John.